Upbeat, curious music starts and fades into the background. What you're looking at is aerogel, the world's lightest solid. So light, this entire piece weighs just 1.22 grams. That's barely more than the same volume of air, which makes sense because it's 99.8% air. Some aerogels are so light that if you took all the air out, they'd actually float in the air around us. I've always been fascinated by this stuff, so I flew out to Aerogel Technologies in Boston to find out, why was it invented? How is it made? What makes it such an incredible insulator? And where is it being used today? To really see its power, we're going to run an experiment. We have two setups, a glass Petri dish and a piece of aerogel. Both are made of silica, but their structures are totally different. We are going to put a chocolate bunny on each and blast them with a Bunsen burner to see which melts first. We're also using a thermal camera that can see temperatures up to 2000 degrees Celsius, so we can see exactly what's happening. Right away, you can see the glass is getting incredibly hot, and after just 1 minute, it's smoking. You can see the bunny is definitely melting and smoking. Oh yeah, there it goes. We've got liquid chocolate. The bunny is even starting to tilt over and Whoa. The glass just shattered from the intense heat. Not only did the bunny melt, but the Petri dish itself failed. Alright now, let's try the aerogel. So how was this incredible material even invented? We have to go back to 1931, to a bet between Professor Samuel Kistler and his colleague. The bet was about jellies, like Jell-O. Jellies are mostly liquid, but that liquid is trapped inside a tiny, solid 3D structure. The bet was, could you remove the liquid from the jelly without causing the solid structure to collapse? If you just let it evaporate, the whole thing shrivels up. As the liquid molecules leave, they pull on each other, and the solid frame, crumpling it from the inside out. Kistler's genius was realizing he could first swap the water in the jelly with alcohol. Then, he placed the alcohol-filled jelly into a high-pressure chamber called an autoclave. By heating it up under high pressure, he took the alcohol to its supercritical point. At this point, the alcohol becomes a supercritical fluid. It's not quite a liquid, not quite a gas. The molecules stop pulling on each other. So when he slowly released the pressure, the fluid escaped without disturbing the delicate solid skeleton. What was left behind was that 1% solid structure, now filled with air instead of liquid, and that is what we call aerogel. Kistler published his amazing discovery in Nature in 1931. Back to our experiment. As you can see on the thermal camera, the bottom of the aerogel is glowing red hot. But after 3 minutes, there's still no sign of melting chocolate. Let's check the temperature underneath the aerogel. It's getting really hot down there. Look, the heat isn't going through the aerogel. Instead, the hot air is flowing up and around the sides, which is why the edges of the bunny are starting to look a little soft. After 4 minutes, the bunny is still holding up remarkably well, considering how icily chocolate melts. Can I touch it? It's not even hot, just slightly warm to the touch right next to a red-hot flame. It is brittle, though. Kistler didn't just stop at silica. He made aerogels out of all sorts of things, like eggs, rubber, and even nitrocellulose. Right here, I have a piece of wet silica gel. It's about 97% alcohol, and I can just carve out a piece. It's rubbery, but very easy to crumble. The next step in making modern aerogel is to replace the alcohol with liquid carbon dioxide. Liquid CO is great because it's not flammable and has a much lower critical temperature. Let's watch it flood in. You can see it's so much cooler on top of the aerogel. Even though the bottom is now at 600 degrees Celsius, that's 1100 Fahrenheit. Notice the bunny is only melting where the flame is licking up over the edge. And, bunny down. It finally slid off. It's not a bad result at all. I'm going to taste some of this chocolate. It's warm and delicious, like fondue.
Oh.
Once the liquid CO has filled all the pores, it's time to take it supercritical.
Oh.
Seeing a supercritical fluid for the first time is a pretty cool experience. You can actually do it with just a hairdryer. As we get close to the critical point, the surface of the liquid gets blurry, and then it just disappears. You're now looking at supercritical CO. In this state, we can vent the CO without damaging the structure. What you're left with is pure aerogel. If you look at aerogel against a light background, it's almost invisible because it's so transparent. But against a dark background, you see a faint blue color. It's blue for the same reason the sky is blue. The tiny nano-sized structures inside scatter blue light more than red or yellow light. a phenomenon called Rayleigh scattering. This also means aerogel is opaque in the ultraviolet but transparent in the infrared. So, what happens if I hold it up to the blue sky? Does it look extra blue? No, it looks yellow. That's because the aerogel is scattering the blue light away, so only the longer wavelengths, like yellow and orange, pass through to our eyes. It's like looking at a portable sunset. Those same nanoscale pores are what make aerogel such a fantastic insulator. You might think that since it's 99% air, it insulates just like air. But it's actually a better insulator than air itself. That's because the pores are so tiny. They're smaller than the average distance an air molecule travels before hitting something else. This makes it incredibly difficult for hot, fast-moving air molecules to transfer their heat from one side to the other. It's called the Knudsen effect. It's so weird because you don't expect something transparent to block heat so effectively. This incredible property is why NASA has used aerogel to insulate its Mars rovers, from Sojourner to Curiosity. The electronics on the rovers need to be protected from the freezing cold Martian nights. NASA also used it for a more exotic mission, to catch comet dust. Particles from a comet were traveling at 6 kilometers per second. When they hit the aerogel, they didn't vaporize like they would against a solid surface. Instead, they burrowed into the low-density material, slowly coming to a stop, which allowed scientists to study them. So will we be seeing aerogel in our everyday lives soon? Well, scientists are working on making it cheaper and more durable. One joke is that when we start building skyscrapers in Antarctica, we'll use aerogel for insulation. Instead of 10 feet of fiberglass, you could use just 6 inches of aerogel. They've already made huge progress. For example, original silica aerogel is hydrophilic, meaning it absorbs water. This piece is now pretty much ruined. But they've developed ways to make it completely waterproof. If you want to see these next-generation aerogels and learn more about their future, make sure to subscribe to the channel. This might just be the start of an aerogel trilogy. Thanks for watching.